either going to grab the camera of the board, or it's going to grab...
No, it's gonna grab you, and then there's a separate video stream for the.
Oh, it's got both.
Yeah.
Oh, nice. Excellent. I did request it.
Yeah, but it shows that it's currently. It knows the class is running right now. But I don't know.
Does it stream it? Like, can somebody pull on the screen?
I don't see it. No, it doesn't stream, it just records.
Yeah. Okay. It means I can't check it.
Yeah,
That's great.
We'd have to see after this class.
I love the debugging. All right, who's gonna take time today? Is it Leon?
I was. Okay,
Who's gonna keep time? Stopwatch, timestamps on the notes. After class, briefly, I'll probably end a couple minutes early, and I'll want grad students to hang around behind and talk to me about how we're going to work the grad sections out. I had a bunch of people request to go from undergrad to graduate, and I hope to the good Lord that you are ready for graduate class. It's going to be more work. You got a stopwatch up? Ready?
Yeah, hold on.
Ready? Go. Oh, channel. There we go. Oh. All right, so we should be recording on 360 with video, and we should also be recording audio just in case that doesn't work. So no matter what, there will be a recording of class. Today, we are going to start learning how to read some assembly. We're going to learn about how the basics of programs work, including the stack and how program flow functions. Hello, hello. Hello, looking good. I like the cow. Thank you.
My friend got it for me from Germany. It was actually
This is German cow.
You get German milk.
It's actually different. German milk.
Because it's in like a. Are they the ones who give milk in precise, or is that Canada?
No. Milk itself is different. Not containers. I don't know if it's standard though.
They don't put the chemicals.
It's got a different enzyme. So there was a optional reading that I dumped into the Discord. Is everybody in the Discord? Yes, good. Grad students, there is a grad channel in the Discord. Please join that as well. We use that for some coordination, and we'll probably do some of the lectures on voice there, or if we can, I'll get together. But we had talked about briefly the Intel manual. It is also on the Canvas now. Has everybody gotten on the Canvas and looked at some of the material that's up there? All right. I'll be storing all of the binaries, the exercises, everything we do in class, and a bunch of supplementary reading up there. But the main reading is going to be from the Intel manual. The one that I posted up there has literally everything. Sometimes they break it up into 4 sections. You used to be able to email them a request and they would give you free books, hard copy. They don't do that anymore. You got to pay for them. That sucks. But this manual tells you absolutely everything you need to know about the architecture. And we are going to learn to read from this manual so that later on when somebody tells you need to work in ARM or MIPS or PowerPC or 6502 or Z80 or anything else you can think of, you'll know exactly how to read those manuals and figure out what's going on. The interesting thing about microprocessors is that we... Oh, you can talk to somebody else.
Yeah, no, don't worry.
Cool. The interesting thing about microprocessors is they all have to do basically the same thing, right? You could run your Mac on an Intel processor, you can run it on an ARM processor. They both have to be able to do the same basic functionality. Every processor needs to be able to do the same basic functionality. The more modern the processor is, the more functionality you'll have, but from a base viewpoint, they've got to be able to do the same thing. So if you learn how to read one, and you understand what it can do, it'll be very easy for you to transfer that knowledge to other processors, okay? As we go through topics, and you have the notes with timestamps, those notes, those topics are pretty much analogous to what you'll see in this manual. If you are one of the grad students, I suggest heavily that you go through and look up those topics in the manual. I am telling you here in colloquial language how those things work, why they work the way they do. This manual will tell you literally everything that the processor provides for those facilities, okay? In about 3 pages, it will have everything. It's a really dense engineering manual, but you'll understand exactly how this stuff works if you do that. And if you understand that, you can take any operating system you like and read the assembly and see exactly how that assembly interacts with that hardware and does what it does, right?
And this is on Canvas with the Discord?
On Canvas, correct, yeah.
Okay.
If you just search Intel hardware manual on Google, it'll pop up too. It's a free download. Today we're going to be looking at assembly using specifically the program that we are going to use. Excuse me, I'm mousing backwards. Actually, I'll just do this. That one, yeah. We are going to be looking at this program here, and this program in C looks like this. Oh,
Maybe more.
that's the thing. All right. Very, very simple program in C. Is everybody comfortable reading this much C? Yeah? Cool. Okay, so what's our C here?
The number.
The number of command line arguments.
Number of command line arguments. Okay. What is this? What's our B?
It's a pointer to a list of strings that are used for, or I guess a list of char stars or char pointers.
Correct. Let's change the terminology a little bit. It is colloquially a list, but it's actually an array, right? So when I say array, it means a very specific thing. What it means is a set of fixed data types, always the same data type. They could be complex or simple. So it could be a single character byte, one after another, in a linear space in memory, or it could be a set of structures. Boom, 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 one after another in memory. In this case, this is an array of pointers. You've got star, star. So it is a pointer to a set of memory, and the primitive there is also a pointer. Okay? So it will be an array of pointers, 4 bytes linearly. This one will happen to be terminated by a null, but you don't have to know that because you already have the count. You know exactly how many elements are in that array. Okay? And then this is going to be a percussion problem, sorry. These pointers are going to point to another array of characters, okay? So it's a string. A string is, everybody know how a string is represented in memory? Yes, anybody not? Excellent. Right, so if I were to write it out, it would be like A, B, C, D, null. Right? Strings are null terminated in C. Okay? And so our argv, I would draw like this. The argv0, argv1, argv2, and in this case, it will be null terminated, but that's not necessarily the case at all times, right? You are going to be using that argc count to make use of this array generally, and that's how it's done in C programs. Okay, then we've got char buff bracket 256 bracket. What's that going to be? Yes.
And then an array of 256 bytes.
It is an array of 256 bytes typed as characters. Oh, I like this. I can just like mark that up. That's great. Yeah, so it's characters. Characters are a single byte, right? And there's going to be 256. What do we know when we see these brackets here as a local variable?
Allocated on the stack.
Allocated on the stack. So local variable, it's on the stack. It is not a pointer, right? It is space on the stack. We're going to see that very explicitly when we draw it, okay? Next line in this C is this guy here. What is this? String copy. A string copy is starts with an F. Function, and it is implemented by libc. Yes. We will talk about linking and loading in the next lecture, but what you need to know for right now is strcpy is a function that a standard library has provided for us. We are going to call it. It does a number of things. How do we know what a function provided by a library does? If we don't know what it does, how do we find out?
Oh, yeah, where you read that.
And yeah, we read the documentation. If you're on Windows, you're going to Google MSDN function name. It'll come up, okay? It's going to have a standard format. On Linux or Unix, you've got man pages. Everybody familiar with man pages, right? Man. Okay, awesome. Other things here. We've got 2 arguments. What order do they come in?
Wait, so if I ordered you like which comes? So
What does strcpy do first off?
it copies the second argument into the first.
Copies the second to the first, okay? This is a standard that we are going to see over and over and over again. Destination, then source. Dest, then source. That's how our assembly looks, and that's how most C functions look. So if I exit back out of here, without looking hopefully better this time than I did last time. And then I just ask main. This is how this is going to look in assembly, okay? And I'm going to break this up into 3 pieces. This guy here, which we will label our function preamble. This guy here, which is our function exit. And then all of this here is the stuff that happens in the function, main. There's only one thing that happens in main. It is called strcpy. This is kind of longer than you might expect it to be. But the reason for that is because we are traversing that argv structure that we talked about just a second ago, okay? So things to note about assembly. 1, each instruction is basically atomic. In a complex instruction set, which this is, sometimes they do multiple things, but they do it in lockstep. That means, unlike a line of C, which may be multiple different things happening, you only get one thing there, and it is strongly defined. And turning this into machine code is direct. There is no compilation. The difference between assembling and compiling is that when you compile, the compiler makes choices about what you've written in changing that into native code. When you assemble, it is direct. There's a lookup table, and the lookup table looks like this, right? So if I want to do a move from a register or memory into another 8-bit register, so single byte move, that opcode's 88. It is always 88, right? That means we can write, if we want to, our own simple assembler very, very easily. And you're probably going to do that if you ever do ROP type stuff, right? You're going to say the gadget that I need is these instructions. I will search for them by bytes, right? It's direct and linear. That means if you live in an architecture quite often, you will start to memorize the opcodes for certain assembly instructions, and you will be able to read the assembly just in a hex editor, okay? The first thing you will be able to learn to read in a hex editor is whether or not something is a string or not, and the reason for that is because strings will always be between 40 and 70 something, right? So 41, hex 41, that's a capital A in ASCII, which is an encoding for single byte characters. If you are looking at Unicode, but you're still looking at Roman characters, it'll be 0041. So it'll be 2 bytes so that there's enough space to have characters in different character sets. So Cyrillic, Chinese, et cetera, right? But we're going to be looking just at ASCII here. So 61, that's going to be lowercase a. Can anybody guess what lowercase b is?
62.
62. Excellent. Yep. And uppercase b is 42. Yep. Cool. All right. So let's talk about what push does. That's the first instruction. And it will get us into drawing our stack. Can people over there read this? Yes? Tell me when I'm blocking you, please, people over here. So we're going to start with ESP here. EBP, our base pointer, is going to be somewhere up here. Okay? When we talk about stack frames, we're talking about the stack for the function that we are in at the moment, and it lives basically in between EBP and ESP. So when we enter this function, our stack frame is from the function that calls main. There is a function that calls main. We'll talk about that more next class. But let's just look at main for right now. So push does two things. The first thing is it subtracts 4 from ESP. So ESP moves down 1. So ESP minus 4 minus equals 4. And then it does move ESP whatever our argument is. So in this case, EBP. Okay? And we'll get to move in just a second. But basically what you're going to see is the value that's in EBP is now here. And we're going to call this the old EBP. That's the EBP from our previous stack frame. What you learn about stacks is everything that you are doing, if you're going to make use of that hardware again, you store it on the stack. Okay? When you're done doing what you're doing and you go back to what you were doing before, you pull it back off the stack again. This works this way everywhere. Okay? It works this way in the kernel. It works this way in every operating system. This is what the stack does. Okay? Move ESP EBP. Okay? That's only going to do one thing. It's going to take the value that lives in ESP and it's going to move it into EBP. So now, after that second instruction, EBP and ESP are now pointing at the same spot. Cool? Okay, so what we have done now is establish the start of our new frame. EBP is now the start of our new frame for this function. Okay? The last thing we're going to do is this sub ESP, and this makes space for our local variables. Okay? In this program, in this function, there is only one local variable. It doesn't matter how many local variables there are. The compiler is going to add the space necessary for all of those locals together, and you'll see one sub ESP, always. Okay? So now we'll say that our ESP is down here. EBP is up here. This is our stack frame, and the distance between the two is how much?
56.
What was that?
256.
Do you think in decimal?
X100.
Thank you. X100. Okay? 100 bytes in between. That's the stack frame for this program. That's what it looks like. Okay? For all the exercises that we do, you're going to be required to draw this diagram at certain points. I'll say, at this line, draw this diagram. What's up?
A question, that old DBP frame, is that frame for a main function that's being called, or what is it?
This guy here, this is main, so this is our main function. Old EBP is coming from the function that called main.
Okay.
Okay, so there's generally a start symbol that gets exported that's called, and that does a couple different things depending on how the compiler and the libraries connect together with the loader. So one thing it might do if there were stack canaries is initiate the stack canary right there and start before it calls main. When we get into more reverse engineering, are you Brad?
Undergrad.
Okay, so we'll look at some reverse engineering stuff and you'll see kind of what happens there, and I'll talk over it next class. What happens before main. All right, so that is our function preamble. We have saved off the things we need to save off, and we have made space for the locals, okay? Interesting thing you may see in newer compilers or compilers that have messed around a little bit more or on Windows is another instruction in the preamble, move edx, edx, okay? Now that is what we would call a NOP, no operation. A NOP, there is an instruction that is actually NOP, that is hex 90. It doesn't matter that there is an instruction that is a NOP, because any instruction that does not do anything, or does not do anything we care about, is a NOP, right? If I don't care what the value of a register is, and I move a number into that register, that could be a NOP, right? So why is that there? The reason that is there is to make the non-changeable portion of the preamble a specific length. So look at just these instructions here. For every function, what's up?
Could you make the assembly a little bit bigger? I'm just having trouble reading.
Yeah, sure. Oh no. All right. I'll try to talk while I'm doing that. Yeah, okay, so the point of those three instructions there, which are always the same, is that if I put that move edx, edx there, man, you're going to mess up all my lines. Let's try 24. Boom. All right, now I got to resize everything and move all my lines around. That's fine. Okay, if I put that move edx, edx there, now I've got a full 8 bytes that will always be the same for every function. Which means I have enough space to replace that with an absolute jump. So a jump instruction that can take you anywhere. And what that provides you is a standard way to hook functions, okay? So if anybody's ever looked at detours on Windows, which is a hooking library, it relies on this. And I will show you how to do your own hooks and how to bypass hooks later on in the class. But if you see something like that, that's what's going on there, right? It means the parts that I know won't change are now 8 bytes. That's why that happens. This guy here is variable by the number, the size of the locals. So that's not going to be something that we can, write over without knowing or saving it off. But the rest of this, we can guess that it's going to be the same, and so that's fine. All right, so we've gone over this preamble right here. Let us talk about the actual meat of the function. I'm just going to go to here. Okay.
I have a question. So you were talking about like the size of the like the bytes and stuff. Why is sub a different size as compared to like push and move?
Okay, so instructions on Intel and some other architectures are variable length. We look at this guy here. Man, all these are just 1 byte. That sucks. That doesn't actually show. Right, so all these are, this is going to be 88 plus 1 argument, right? But some of them have a fixed number of larger bytes there, or they take a different argument size, and so they are different sizes. And the reason is because we want to maximize our use of code cache, right? So if we make the common instructions as small as possible and the less common instructions larger, then we use less space in our code cache, right? So that means that instructions are not necessarily aligned on Intel. If somebody tells you that instructions are aligned on an architecture, it means 2 things. 1, the instructions are all the same length. So if you look at 32-bit ARM, all the instructions are like 4 bytes, right? So the instructions will always be on 0, 4, 8, C, 0, 4, 8, C. and it will not let you execute an instruction on like an offset of 3 or 1, right? But Intel will let you execute instructions at any offset, which is a benefit to us later, because if we can't find the gadget we want in actual instructions that somebody wrote, we can misalign instructions that exist and get arbitrary ones. Okay. But that is not really what we're doing here. What we need is that, you see how sub ESP100 is specific to the function itself? It's specific to the size of our locals, right? When we are looking at putting a hook in, we want the things we are overwriting the hook with to be the same for every single function. Since that sub ESP is not the same for every single function, it's not something we can reliably overwrite without saving it off, which is a pain in our butt. We could, and I'll show you how to do that later, but that's why it's like that.
So are we writing like the knob inside, or is that just
Writing the knob inside?
Yeah, because like you're saying how like we want to have it like allocated or space allocated a certain way, and have it uniform as opposed to like including sub, which is not a uniform instruction size. So we have like the knob to
Yeah, BDS. Yeah, that's our knob. So that just happens to be a 2-byte instruction, and we need 2 bytes to get to 8 bytes. So it's just something that they plug at the top of every function so that you have that space.
I see. Okay.
They're making space. They could just put 9090 there, but they don't use immediate BDS for some reason. I don't know. Okay, so let's look at this guy here. The C that we are compiling down is strcpy buff argv1 question mark? I think that's right. Yep. Okay. So we push arguments in reverse order on the stack. So when we finally get around to these pushes here, which are the 2 pushes that put our arguments on the stack, eventually it'll be argv1 will be first, and then buff will be below that. Okay, so buff will be the closest to the actual frame we're looking at. This calling convention is standard call. Okay, it is standard call in x86. That means that arguments to functions are pushed onto the stack in reverse order. That is a convention. Okay, we could write a compiler that pushes them on backwards, and as long as both sides of the function are expecting them to look that way, that's fine. Okay. But since we are calling a library call, that library gets to tell us what the calling convention is, right? If libc expects standard call and we give it something else, it's not going to function right? So we have to live with the library. So that's standard call. On x64, standard call actually uses a bunch of registers to store the first 3 arguments and then the stack after that. Okay? On x86, we would call that fast call. So if you see a function that's got in C that's got something in front of it that says fast call, that means this function is going to take just 2 or 3 arguments. You're going to see them in ECX, EDX, and EDI or something like that, right? So if you see that in reverse engineering, that's what you're looking at. In this case, standard call. Okay, so let's break this down a little further. This guy here, this is going to handle argv. And this guy here, this is going to handle buff. So let's look at the argv one first. We are using move here, and move gives us a couple fun things we can do. We can move a register into a register. We can move memory into a register. We can move memory on which we have done some math into a register. What you see here is one of the simplest cases of memory, as denoted by these brackets. That means whenever you see those brackets, go there, get the memory at that place, give it to me. Use that as the argument, okay? We know the size here is a D word. Now that's kind of a weird way to put that. A D word is 4 bytes. This is a legacy name. You've got bytes, you've got words, you've got D words, and you've got Q words. This is not actually how this is supposed to go, but it is a convention that we've learned to live with due to history. What a word actually is the size of the bit width of the processor. So on a 32-bit processor, a word ought to be 4 bytes, 32 bits, right? Here we say it's a D word. Why? Because we started writing GB on a 16-bit processor. And so they decided a word was actually 2 bytes, and now a D word is 4 bytes, and a Q word is 64, right? But you might also see another architecture that says word size, and what they actually mean is the bit width of the processor. So do not trip over that. On Linux and Windows, though, D word is going to mean 4 bytes always, no matter what architecture you're sitting on. Okay? So we are going to move into the destination of EAX, but where we are going to move it from is what EBP is pointing to plus the number C. So that's a little example of the kind of math that we can do inside those brackets. Okay? The full gamut of math that you can do inside brackets looks like this. Reg plus index times size. Okay? So a register generally stores a base pointer to, say, an array of structures, and the structures are going to be n bytes large. And so if I wanted to get the third element in an array, I would say base pointer in my register plus 3 for my index times n for my size, and it would automatically give me a pointer to that element in the array. That's why that exists the way it does. And there are a lot of data structures that get referenced that way. The array of structures is the thing that computers work on, okay? In this case, we're doing the simple case of adding C. So let's talk about how to use our base pointer in reference to a stack frame. The base pointer is defining the top of our stack frame. If you see EBP, you want to write this down in your notes, minus some number, n, that's going to be a local. Okay? If you see EBP plus some number n, that's going to be an argument to your function, not to a function you're calling, to yourself. Okay? Everything in this above the stack frame comes from the last function. Below the start of the stack frame, those are locals. Okay? So you should be able to look immediately at a reference from EBP and see, am I talking about a local? Am I talking about an argument? So in this case, I am talking about which?
Argument.
Thank you. All right. One other thing we need to add to our stack frame. Our very favorite pointer in the world, the return pointer. Now, we have not gotten to call yet, so we haven't talked about this. But when main is done, it's going to return back to the function that called it. How does it know where to go to? Well, we stored the next instruction after the call on the stack. Okay? Call will do this for us, and we'll talk about it as soon as we get here. Just know that it's there. So then above that, you're going to have the first argument to main, which is, in this case, argc, right? It's going to be our argument count. Argc, and then above that will be the second argument, the array called argv. That's right. V. It is of a type that is standard, right? It is known as var args in C, so anytime you have a function that takes some multiple number of arguments, say like printf, that can take an arbitrary number that is sent as a var arg structure. That's what a var arg structure looks like. That's your first var arg. Okay. So if I say EBP plus C, here's EBP plus 0, here's EBP plus 4, here's EBP plus 8, here's EBP plus C. So what have we moved into EAX right now?
RV.
You're going to say the same thing?
I was going to say RC.
Oh, no, you're wrong. You're right. Would have been better if I had that, sorry. Okay, so now we have a pointer to argv in EAX. If you look at our C code, argc in the C code is not referenced, right? This is the only line in main that we have. Only argv is referenced. If you don't give it enough arguments, it's just going to crash in a second, and we'll show you when it crashes. So this program is assuming you sent it the right number of arguments, being one argument. Interesting other point here. The next thing we're going to do after we get argv, a pointer to our array of pointers, is we're going to add 4, okay? Now, we are adding 4 bytes to that, so we're going to...
I have a question about the moves. So like, the D word pointer, I know like it specifies like how much space it is, but isn't the EAX already like 32 bits? Why would you need to specify the space of what you're getting?
You don't actually, you are correct. This is just a convention of how GDB is showing you the instruction.
Oh, I see.
Right? If you were to look at this, say in WinDebug, it's not going to tell you keyword pointer. It'll just assume you know that because the destination is 4 bytes, it's going to be 4 bytes. Caveat, you might see move ZX, which is 0 extend, which would mean something like move 2 bytes from memory over there and pack the rest of the register to zeros. Okay? Or you might see sign extend, which we haven't talked about assignedness works, have we? Let's do that real quick. So we've got a number, 0x, AA, BB, CC, DD. There is a delineation point in hex numbers, and that is in the high order byte 80. When you see 80 or above in the high order byte, what you know is that the most significant bit in the number is set. So if you are 7F or below on a signed number, you're positive. That's a plus number. If you have 80 or above, that's a negative number, okay? And it works the opposite way you think it does. Here's how. If I am adding 80000 something to a number, it's going to roll over, but it's only going to roll over by 1, right? So that's going to be a -1. The larger the negative number is, the smaller the negative number it is, okay? The bigger the negative number it is, the smaller the negative number. Bigger. You know what I mean, right? Thank you. So the biggest negative number you can have is 8000000, and the smallest negative number you can have is FFFFFFFFFF. Yeah, so assign extend would say, treat this as a 2-byte number. What's the most significant bit on that? Extend that bit all the way across. So if it's a 1, everything becomes a 1. If it's a 0, everything becomes a 0. So that would be move SX, assign extend. We are not going to go over every single function in Intel. You are going to have to read a lot of instructions out of that manual. The reason we're not going to go over them is because many of them are very rare, right? They're not necessary in most contexts. Most of the instructions you're going to see are going to look exactly like this. Add, move, push, load effective address, call, jump, add sub, stuff like that, okay? We'll talk about branching a little bit later. So we've added 4 to this, which means we've gone from argv.
Sorry, one more question before we leave the move.
Sure.
I've been looking at the developer's manual, trying to piece together which move instruction specifically this is. There are like 3 dozen.
Yep. Yeah.
And I have a guess, but I'm not sure.
So this is a 4-byte, right? And it is from a memory address to a register.
Right. I mean, like if you click over to the table, which one? Because there's one that's move double word at sec offset to EAX, which gives me good vibes.
Okay, so there's no segment selector in that. It's going to be actually this one right here. Right?
Yep.
So we're going to move to a 32-bit register from either a register or a memory of 32-bit. And that's the one you want. So if we were looking at an sreg that's from a segment selector, we talked briefly about segment selectors, and that was part of the optional reading. So I probably suggest that people go back and take a look at that section. Segment selectors are not often used in modern operating systems except for very specific things, but they provide you the ability to have separate virtual memory spaces for separate pieces of the same process. That's generally not used except for like process environment block, thread environment block stuff. So if I want to store metadata about the thread that's running right now, that's going to be its own pointer. I get to that with like the GS segment selector. If you ever see somebody pulling in GS : something, that means they're reading from the thread environment block. You can look at what the thread environment block structure is and make use of it. And when we get to shellcode, we will do that. All right, cool. So that add EAX4 is adding, we're incrementing a single pointer on that array, okay? Difference between C and assembly. In assembly, there are no types, right? In C, there are types. If I say add 4 to an array of pointers in C, I'm going to increment by 16 or 10 hex bytes. If I add 4 in assembly, I'm actually adding 4, okay? I screw this up all the time when I write C. Sucks. So now we've got a pointer to argv. Now remember that array is a pointer of pointers. So we want to get, rather than being at the second entry in that array, we actually want to get the pointer out. So we do this again, and we move the pointer to the string that is our first argument there. Okay, so why did we have to increment 1? What's at argv0?
The program name.
The name of the program, right? The name of the program is always the first argument. A lot of pieces of software will actually make use of that to check the name of the program. So if you are writing some malware, please feel free once the program starts to make modifications to argv0 as you see fit. And then it could be whatever you want it to be named. We're not doing that in this case. We're pulling out that first argument to the program. Okay, so now we've got a push. And that push is the pointer to our arg. Okay? And so ESP has been subtracted by how much? G. And so this number has also changed. Okay. Now we get our first exception here to our brackets, which is load effective address. Load effective address is like if you wanted to abuse the math functions of move, but you didn't actually want to pull the memory. You just want to be able to do the math and get the pointer. Okay? So when you see load effective address, even though you see the brackets, you're not getting the memory. This is the only instruction like this. Every other time you see the brackets, you go there, you get the memory. In this one, you do the math. So this is saying, take EBP, subtract 100 from that number, store that in EAX. Okay. Why are we using load effective address here and not move? It has to do with the answer you provided previously about how buff with brackets differs from a pointer.
Is it because string copy takes a pointer to the buffer result?
That is correct. We can only send as an argument. This is an interesting point. You cannot send a structure or a complex data type as an argument, right? Every argument is how many bytes? 4 bytes. So if it's going to be more than that, you got to send a pointer to it, right? We don't have a pointer to buff. Buff is a local, right? All we have is 100 bytes of space. So we need to make a pointer to it. The load effective address allows us to do that. So we are saying EBP minus, right? So what does that mean? We are referencing what from EBP minus? A local. Yeah, it's not an argument. So we know it's a local. So we can say, oh, we know that's buff. And we're going to move that pointer. We're actually creating that pointer and moving it into EAX, and then we're going to push it on the stack. So now we've got, wait, and buff. And you can see that they're pushed in reverse order. Buff is the first argument to stir copy. Our RV pointer, 1. That was the first thing we pushed. It's going to be farther away, okay? So we've now set up all the arguments to this function call we're going to make, and we're going to call. Call is spectacular. Call does, what's up?
Sorry, just to clarify, the reason we're using load effective address is because the buffer is a complex.
There's a couple of reasons. So that's one of them. It's also a local, right? So when we did sub ESP100, we made space for buff, but we didn't make a pointer to buff, right? We got argv as a pointer, so we just took that out of the array. We don't have a pointer to buff, we have to make one. And load effective address makes a pointer to it, basically, right? And then we can push that pointer, right? If we had a pointer somewhere else, we wouldn't need to make one, but we do, so we can make one. And that's very often, the only time you're ever gonna see load effective address in most circumstances is going to be in that case.
So you could, like, it's effectively the same as moving EVP into EAX and then subtracting 100.
Exactly, yep. Back in the day, various registers were attached to various pieces of hardware in the processor directly, which meant that they had speed advantages. At one point in time, and before that, they were the only registers that would be able to get the output certain pieces of hardware. So EAX is named A because it is attached to the ALU tradition, the arithmetic logic unit, right? So if you were going to do math, it would always be put in the EAX no matter what. You wouldn't specify destination. Most of the registers' names actually have a meaning like that, right? And they're usually legacy, but you will see some instructions that still only function in specific ways with specific registers. When we look at rep function instructions, which are repeating instructions, ECX is used, it's the only thing that's used as a count, right? So you'll put ECX to some value, and that instruction will repeat ECX number of times, decrementing it every time around. You cannot use any other registers for that. So if you have something in ECX that you need to use, but you need to call that function, you push it, you call the thing, and then you pop it back off of it. Or you store it in another register you're not going to be using. Okay? Yeah, so EAX is a couple of functions like that. So, where were we? All right, we're at call. Let's talk about call. Call is going to allow us to create a whole new stack frame. And so when we're done with stir copy, what's the next instruction that's going to get run here? So,
the add.
Add. Reference it by offset from main.
Plus 30.
Main plus 30. Thank you. Yeah. See this here? This is going to be very helpful to you. There are two ways to reference instructions here. One, you can say, use the actual address. So if I want to disassemble something in the debugger, you see I did disass main. I could just as easily have done disass 0804 9166, right? If I want to actually disassemble from here, I could say disass main plus 30, or I could do 0804 9184. Small digression, we have turned off address space layout randomization, which is a mitigation on these systems. You will thank me for that. We will learn how to bypass it later. But for now, here's why it's useful to you. You see this 0804? The programs you run will always be loaded at 0804, which means you can look at pointers in memory and say, oh, that's a pointer to a code page, right? Our stack will always be at, this is not running, so I can't dump it, but it'll be at OX, BF, FF, something, something. Okay, so if you see BFFF, you'll be like, oh, that's a stack pointer, okay? Later on, when you get into ASLR, you will be able to do those translations in your head. You'll disassemble something. You'll be like, okay, I see the code pages are loaded here. Now what I'm going to do is snapshot my virtual machine that I'm working on so that that doesn't move, and I'll just know in my head that that's where my code pages are, right? So a lot of the time when I work on a program with ASLR, I'm always working in a virtual machine. My target is always in a virtual machine, okay? And I use snapshots goddamn constantly. The reason is is because even if the addresses are moving around, if you start the program once and you snapshot it, they're not going to move on you while you're working, right? That doesn't mean you're going to rely on them in your solution, but it is going to make your reading much more easy, right? When you're looking through memory, if you know where the code pages are, you'll be like, oh, that's a vtable pointer. Oh, that's this, that's this, that's this, right? You will start to be able to read the hex if you understand the structure of the program and you keep these things consistent, okay? In 2 classes, we're going to do this example as a lab and we're going to exploit it. And so we're going to be digging pretty heavily into the debugger and looking through the memory, and you will see what I mean when I say that. You'll be able to say, oh, I can tell that this is this type of thing, and I can tell that this is that type of thing, just by looking at the numbers, okay? So call. Call does 2 things. It can be broken down into 2 basic instructions. One is a push instruction. I'm going to make some more space to draw. One is a push instruction. And what it is going to push is the address of the next instruction to be run. So it'll push main plus 30. It knows how large call is. Call is a fixed length. This is an absolute call. There are also relative calls. Here's the difference. An absolute call takes a full-size pointer, 4-byte pointer. In this case, the pointer is 0804-9040. That is to the loader of strcpy on the PLT, which we will talk about in the next class. But it's an absolute call. It takes a full pointer. A relative call would be call where we are right now plus or minus some value, right? So if I wanted to write code that did not rely on absolute addresses, I could do that very easily, right? And we will abuse this in our shellcode later on. So that's an absolute call. First thing it's going to do, push the next instruction address. So it's going to push main plus 30, we'll say. Okay, and then the next thing that it's going to do is jump. And it's going to jump to strcpy. What the heck is jump? Jump is this. Some value, either a register or an immediate value. An immediate value is a number. So in this case, we are jumping to an immediate value. Okay, so if I say there are three types of arguments we can have. We can have a register, we know what that is. We could have memory, that looks like an argument that's got brackets around it, maybe says D-word pointer. And the last one is an immediate value, which is just a fixed number. So a byte, a word, a D-word number, okay? EIP is our favorite register. What does EIP do? It has a fixed rule, and that rule never changes no matter what. It is RIP on x64. It is PC on many MIPS, PowerPC, and ARM. What's it do?
It's the instruction pointer. It keeps track of where you are in the program.
Yes. It is the instruction pointer or the program counter if it's PC. That is just a pointer to the next instruction that's going to get run. Okay? So this guy here will be the value of EIP after this call. And what we will have here is our ret to main. So that is a return address. That is how return addresses get put on the stack. Okay? And our ESP is here. And inside strcpy, you're going to see the same exact thing that we just did here is going to take place there. It's going to move the EPP and ESP down. It's going to make its own local space. It's going to do some work. And then it is going to call the ret instruction, which we have not gotten to yet. And the ret instruction is going to do the opposite of this. It's going to do pop EIP. Okay? So we call strcpy. Strcpy does its work, and it comes on back. Now I can tell something about how the compiler has compiled libc from looking at this right here. Okay? So we have basically when we return from stir copy, ret's gone. That's been popped off, right? It's been popped back into EIP. Now here's ESP. And we've got some garbage on our stack. If we were calling stir copy in a loop and we did not handle this garbage, the stack would grow, and the stack is a fixed length, so eventually it would hit the end and the program would crash. Okay? But in this case, we use add ESP8. Now, we're not popping it off into anything. We don't care what happens to these arguments anymore. We don't even have to delete that memory. We're just moving ESP. And that tells us anything below ESP is basically garbage. It may or may not be valid. There are techniques. If, say, someone has a local variable that they're going to possibly use in an uninitialized state, where you can paint the stack with garbage and initialize that variable for them, right? So that's another type of attack we might look at, but basically, anything below ESP is now garbage. It's no longer part of our stack frame. If we were to call another function, we just write right over that memory, right? Every time we did a push. That add ESP8 clears that up for us. However, there's another way to clear that up. When you are looking for ROP gadgets, this will be useful to you. It is called retn. And what that does is takes an argument, which is a number. So if we wanted to get rid of this, instead of having stir copy call ret, we could call retn8. And what it does is it pops EIP off, and then it adds that number to the stack pointer. That's all it does. It does it all in one go for you. Okay. But it's basically exactly the same as this. All right, so now we are at the final exit portion of our function. Move EAX 0, leave, and ret. This stuff is going to roll back our stack frame and hand execution back to the function that called us, okay? The first thing we see is the move EAX 0. So this is not written in the program. It probably should be. It probably throws something of a warning, but I probably have those turned off. Normally at the end of the function, if you're not returning anything, you'll see that, right? Every function returns a value. Every function returns a value. Even if it doesn't return a value, even if it's void, you cannot rely on EAX not getting stopped. So if you call a function in your assembly, and you're like, oh, that's cool, EAX will be fine, it's not guaranteed to be fine. Your value in EAX is probably going to get stomped on. So in this case, it was an int, there it is, int main, but there's no return. So the return value is 0. The return value is always returned in EAX. Okay? On x64, it's returned in RX. Okay? In ARM, it's returned in R0 or R1. Right? But it's always the same. And in this case, that's what's going on here. We are setting our return value. Not strictly necessary. However, the loader is going to make use of that, right? If you run this program on a Linux shell and you try to see if the program succeeded or not, it's going to tell you it succeeded. That 0 is a success. Any number is an error number, right? So you could use the shell to determine whether or not this program ran properly or not, and it would say, yes, I ran properly. Later on, it will not run properly, but for right now, it's running properly. Okay? So the next thing there is leave, and leave is another complex instruction that we could write as 2 other instructions. So let's see if I can do this. Leave is basically, it's going to be move ESP EBP, pop EBP. And that unrolls our whole frame, okay? So right now, we've got 100 bytes in between ESP and EBP. And we're going to basically wipe out all this. All this is going to become garbage because it's going to be below ESP. Now ESP and EBP are here, both at the same place. And then the next thing that it does is pop EBP. So now, this is gone. ESP points here, and EBP now points way up there somewhere in the previous stack frame. So the start of the loader, that old EBP, everything we use, we've got to restore back. Everything that needs to be restored back is going to be stored on the stack, always. Cool? So we're unrolling everything we did, and then our last instruction is ret, and ret is going to pop the IP, right? So when we leave this sucker, we have returned our execution to the caller of main. ESP is sitting right below the arguments, which is basically where we found ourselves after the call of stir copy, right? And that's that. Now it goes back to executing what it was doing before. Now I'm going to go look through my notes and see what things that I forgot to tell you about during this exercise. Sorry, timers. We talked sign and unsigned. We talked all the instructions we talked about. We talked about registers, immediates, memories, and complex stuff. We talked about functions, the stack, calling conventions. In short, we talked arguments, locals. What's up?
So when the function is done, it doesn't clear up the arguments, or?
Nope. No. So just like us, sometimes, depending on your compiler in the library, it will call ret-n and clean up the arguments. But sometimes, the function that did the calling has to do it itself, right? And that's what that add there is. So when we came out of stir copy, our arguments were still there. When we come out of main, our arguments for main are still there. Basically. And the loader will probably do add ESP8, probably the next thing it's going to do. Variables that transcend functions. Okay, so all of the variables that we've looked at in this example live for the duration of their function and not beyond, okay? There's one, what's up?
Couldn't you overwrite EBP for when you hit leave to change where the stack is?
You can do literally anything. So yes, yeah, you can do anything the processor lets you do. And yeah, I'll give you some examples of that. What was I saying? Oh yeah, okay, so our variables that we talked about, they live for the duration of the function. There's an example of this not being the case. When we call stir copy, there's a pointer to buff. Buff lives in our stack frame, not the other one. Now because stir copy is called from main, and the way that a stack frame looks is always the same, unless there's recursion, in which case you will have chunks of stack frame that always look the same. We know that buff is not going to go anywhere while stir copy is running, right? Unless something crazy happens, we get a signal handler with a long jump we'll talk about later. We know buff is going to live as long as stir copy is alive, because stir copy was called by us, and there's no way for the stack frame to unroll that for it to become garbage, right? The other way to have this happen, where you have variables that live beyond their function, is to not put those variables on the stack, but to put them on the heap. The second half of this course is going to get very deep into heaps, how they work and how to exploit them and how to think about exploiting them. But for now, just know those are our two types. What's up?
15 instruction do?
What is what?
Instruction plus 15.
Main plus 15?
Yeah.
So when we get to here, what we have is we are looking at that argv array. So argv0, argv1, right? When we go EBP plus C, we have a pointer here. That's what's in EAX right here. This is EAX at plus 9, okay? We add 4 to that, so now EAX is here. That's EAX at plus 15. And then what we say is what we want in EAX is this pointer, which is a pointer to the string. And so we do this. What memory lives at EAX? Pull that out, put it in EAX. Now the pointer to that string is in EAX. Cool?
Yeah.
Cool. We talked arrays and arrays and pointers. We talked a little bit about functions and functions calls. Let's talk about NASM for a second. Let's learn a tool real quick, because we have, I'll take 5 minutes and do that. Take 5 minutes.
Yeah.
At the end of this, I'll dismiss everybody except the grad students who I would like to come down here to talk to me about how we want to structure what will essentially be a seminar. I've got a couple people that already have jobs and want to work on very specific things, and I'm going to facilitate that. So I want to talk to everybody and see where they're at, what they want to learn, and kind of what level they're at. But let's do this first. You have now learned assembly. Let's learn how to write some stuff in assembly, either full programs or pieces of programs that you may want to use. I'll put this on my lap. Yeah, there we go. Okay. So here is a real small chunk of assembly that I wrote for our first lab in order to provide you some instructions. To return to later on. That will make more sense later, but let's just look at how this works. The first thing we write at the top is the section. We're only going to be writing for this just a chunk that I want dumped into an object that I can load as shellcode or in a program that exists. So the only section we need is a text segment. Dot text is where code lives, okay? It's not dot code. If you are to pull up Ghidra or IDA or GDB or ObjDump or Binary Ninja or anything else, the section will be named dot text. That's where all your code lives. So what I'm saying here is everything that follows in this file is code. I could put a bunch of arrays up there in a dot data section, or if it's a read-only dot R data. There are other sections as well to do specific things. This is just code, okay? I'm going to say global underscore gadgets, and what that means is I want you to export the symbol. The symbol gadgets right here is not just for me to reference in my code. You need to store that in the object that comes out so that somebody else can reference it by name. So when I build our lab that we're going to go through in 2 classes, you'll be able to do disass underscore gadgets as a symbol, just like you could do disass main, and it'll dump this out, because this object is loaded in there, okay? So here's the actual symbol. This says export it, but this is the actual symbol, and it's just named with a colon, and then you just write your assembly there, okay? You can write the assembly wrong, it will not care. As long as the instructions are legitimate instructions, they could be absolute gibberish. But because it's a lookup table and not a compiler, it's just going to be like, you want to jump ESP? Good. Here's the bytes. And it dumps it out in bytes, okay? So when you actually run NASM over this file, oh, I didn't even do it here. NASM has a bunch of output options, okay? So we'll talk about file formats next time, but basically, I can have this sucker output as an object that can be loaded by like a static linker loader, right? So I can make that .a, which is going to become a part of the program itself. It'll become embedded in the program. I can make a .so, a shared object, which is like a DLL on Linux. And what that means is it can be dynamically loaded, right? So you could call load library and load that thing up, and then reference gadgets, and it'll handle that for you. It'll give you the headers on the file to do that, right? The other way that you can do it is just direct output. And what direct output will give you, like a raw file, is just the bytes for jump ESP, just the bytes, right? And so this will be useful for you to write shellcode with. We don't need any headers. We don't need any section help. All we need are the bytes for that instruction. So if I do X dash capital C dot slash y A. Okay, so this one is set up as a linkable, statically linkable object. So it's got a lot of stuff in it extra. If I were to do this as a raw output, all you would get is this right here. How do I know that this is what I would get? Well, I know that FF is a jump, is a register jump. It's 1 byte. So FFE4 is jump ESP, which is the first one. FFE5 is jump EVP. That was the second one. 89CC is, so 89 is a move, right? We looked at the table, we saw 88 was a move. So even if you don't know what 89 is, you'd be like, well, that's, how many moves are there? There's like 50 of them in that table. So 89 is probably a move too. It is. And it's a direct register move. CC contains the information for both of the registers. So this is going to be move ESP ECX. And then C3 is the single byte instruction for ret. So yeah, jump ESP, move ESP, ECX ret. Okay. If I did that as raw, you would only get those bytes and nothing else, none of the other garbage. This guy allows me to link it into the program. And so the reason that I'm putting this stuff in here is because the way that people generally exploit stack-based buffer overflows in the simple case is to return to their shellcode on the stack. That's dirty for a number of reasons. Even if the stack is executable, you should not execute on the stack because the stack moves. It moves with the operating system, it moves with the user, it moves with the environment variables, it moves with the arguments of the program, right? All of those things are above you on the stack that the loader sets up. And so your stack, even if you're running it, doing a CTF on somebody else's machine, but nothing else has changed, and there's no ASLR, that stack's going to move around like crazy, right? So we don't return to things that move. We return to things that are stationary. And code pages, relative to where they are loaded, are stationary. When you load a library in memory, what it is on disk as its sections, so its whole text segment, that's going to be in memory verbatim. It doesn't matter if you're only using 1 or 2 functions out of it, the whole thing is going to be there, okay? And so if I know where something is relative to the start, it doesn't matter when the start moves, I still know where my offset is, right? That offset is static. So we always rely on text segments when we can, and we never rely on addresses on the stack. Okay, so I'll be providing this to you from the jump. We're going to do it right, not like amateurs, like professionals. And so that's why this is there. But this is basically how you use NASM. If you want to know, if you are fixing shellcode, and you will have to do this very often, say, I am jumping into code. I'm going to execute on the stack. I didn't return there directly. I returned through a code page. Cool. But what's going to happen is sometimes your shellcode will push things onto the stack as well. And if your stack pointer is sitting in the middle of your shellcode, when you jump there, and then you call a function in your shellcode, what's going to happen?
You don't have a stack pointer.
No?
It's going to overwrite your shellcode.
It's going to overwrite your shellcode, right? If your stack pointer is in the middle of your code, and you call a function, you push onto the stack, you're going to trash your shellcode, right? So what do? The very first thing you do is you write a custom little sub at the front of your shellcode that says sub ESP200. Just get your stack pointer out of your code. That's it. And then run your shellcode, it runs fine. But what you will need to do is know how to write sub ESP200. And you probably don't have all the code tables memorized yet. So the fastest way to do that is to pull up a little NASM file, write sub ESP200, compile it into a raw output, and then hex dump it and look at it, right? Or use objdump is another way you can look at it. It'll give you the bytes plus the disassembly so you can be sure you're looking at the right bytes, right? ObjDump is going to be seriously useful if you're not using like a fully fledged disassembler. We are now over time. Sorry about that, but I also think our recording's going to get cut off now. So we'll talk about the rest of this stuff on Thursday.